In this video we are looking at change of variables in triple integrals. So this is the equation that we are going to be looking at, and it looks scary, but it shouldn't, okay? And that's because it's just sometimes books like to write things like this, but actually it's very simple. So let me reassure you. Remember in 2 dimensions, when we were doing integrals, for example, in polar coordinates, that was very easy to do, right? And we just had to do 3 things. We had to change the integrand from xy into polar coordinates, so for example rho and phi. We had to change the limits, so for example if we were integrating on a disk, we had to find the limits for rho and for phi. And then we had to change the differential, which there were many ways of doing, by geometrical intuition, following the recipe, or looking it up on a table. Yeah. So these 3 steps, changing the integrand, changing the limits, and changing the differential, they are very easy to understand, and they can be summarized in a long equation. Rather than listing the steps, we can actually summarize in this equation. Okay? So this is an integral in x and y, and now this is the integral on the new coordinates u and v. So this has 3 things. First, we changed the integrand. So f of xy, wherever there was an x, now we substituted x as a function of u and v. So that means that we are substituting the values of x in terms of u and v. Okay? So for example, for polar coordinates, x equals rho cosine phi and y equals rho sine phi. So if the integrand was, let's say, x squared plus y squared, the new integrand would be f of rho cosine phi, rho sine phi, which would be equal to rho cosine phi squared plus rho sine phi squared, which is equal to rho squared, because cosine squared plus sine squared is 1. So the integrand would change from x squared plus y squared to rho squared. So this is encoded in this notation here. Next, we remember to change the dA. So what previously was dx dy now has become the Jacobian determinant, the absolute value of it, times du times dv. And we remember that this was equal to dA. Yeah? And finally, the third step is that we have to change the limits. So first we were doing an integral on the area A by using limits in x and y. And now we are doing the integral on the same area A, but we need to write the limits for u and v. For example, if we are in a circle and we are using polar coordinates, the limits are rho from 0 to r and phi from 0 to 2 pi. So this is how we can write a summarizing equation for change of variables in 2 dimensions, and we already did problems about that, and it was not scary. So we just have to do exactly the same equation, but for 3 dimensions, okay? So we just have to add z here, dz, we will have to add z of uv here, the Jacobian will be a 3 by 3 matrix, and we'll have du dv and dw. And that is exactly the equation that I showed you at the beginning, okay? So it is not scary, it simply includes the 3 steps. So changed variables in the integrand, two, change the limits, which is encoded here, and 3, change dA. In this case it's dv, because now it's a volume integral, right? And dv is given by the absolute value of the Jacobian determinant of a 3 by 3 matrix, because now we have 3 original variables and 3 new variables. So if we do all of the possible partial derivatives, we have 9 possible combinations, times du dv dw. Okay? So it's not a scary equation. It's actually quite simple. Also, in practice, I'm never going to give you like a general change of variables that looks weird. I'm always going to use either spherical or cylindrical coordinates. And therefore, everything becomes very easy in that case. See you in the next video.